The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
The final presentation of this first of 2 sessions is going to be given by Mike Kreger, who is a student once of Meta's, but now a colleague at Purdue University. Mike, welcome.
Great.
Good to see you.
Thank you, Jack. This one may be a bit of a more of a stretch compared with some of the others and how it relates to the PCA book. Initially I thought about talking about some of the things that I've been involved in with beam column connections, but I knew Jim would do a much more thorough, extensive job of discussing that. So, okay, I'm going to talk about something that I'm currently working on. This is not finished yet. We're wrapping it up, trying to wrap it up now. And what has this got to do with the PCA book? In 1981, Meta gave me a copy of that text. And for me, it became, early on anyway, as I was starting to work in this area, a book of details. It emphasized in my mind the importance of details. So this was the original title that I gave, I think, Gustavo when we first got started. And I should point out along the way, for those of you that don't know, this project became kind of the marriage of 2 guys, one working in structural steel, one working in structural concrete, to make this happen. And so if you don't know my colleague Mark Bowman, he's the structural steel colleague that I've collaborated with, and Ramesh is our graduate student. So if I had the chance today to give this a new title, I would have said the devil's in the details. Meta, everybody here has probably heard this numerous times, but the first person I ever heard that from was Mete A Sozen. And as we got into this project, I don't know if any of you worked the way I guess I have in the past on some projects. You think you know what you need to do when you start, and as it unwinds, as it evolves, we realize, I don't know about this, I don't know about that. And because this was so far removed from things I had done before, there was a lot that I didn't know. And I'll highlight what some of those are here along the way. So I'm going to touch on some of these details that we looked into and ultimately show you the most recent test, or results from the most recent test that we conducted. So Charles Pankow Foundation funded this. I better make sure I mention all the folks that contributed. Canron fabricated all of the steel plate that we used in these specimens. You get a sense of how much that was as we go along. The origination of this idea came from Magnuson Klemensick and Associates, and I'll talk in a minute about why would you want to do something like this. And then I'd be remiss if I didn't mention a friend, Mike Engelhardt at UT Austin, who we contacted more than once to talk about welds. For those of you that don't know, Mike was one of the key folks that worked on the non-ductile ductile steel frame problem after Northridge, and was very involved in the welding processes that needed to be used to correctly construct those ductile frame connections. So why use a composite core wall? This is just an example, but this building that you see here in the middle of the slide, and you can see who its big brother is over to the right. That's what was formerly called the Sears Tower. Very common for 40, 50, 60-story buildings today to rely on a central core wall for lateral force resistance. and hang off of that, very often a steel gravity frame system. Well, if we look at what this looked like while it was going up, one of the problems that folks working in this area have run into is the speed at which this core wall can be erected, potentially anyway, holding back the speed of construction of the overall structure. And there is also additional concrete work that has to be done in casting this gravity frame system that's hanging off of the core wall. So they were looking for a way to construct the core wall system much more rapidly and to maybe uncouple some of these different trades or groups that have to work on the job site and that come and go and aren't there every day and available to, for instance, cast concrete at a moment's notice. So I think most of you are familiar with this, but here is a typical core wall. We stole off of some plans off of building that MKA had worked on in the past. And you can see it's made up of very typically flanged sections, and it becomes the elevator core. Now, in the very early going, what was envisioned, and there's some stuff here that we did not end up using in our tests, but was to put this wall together out of a series of plate assemblies. And the plate assemblies, the outer plates, are tied together with these things that are colored red here, transverse rods. And in these drawings, it also shows a fairly minimal amount of mat reinforcement inside the wall. In our tests, we ended up not including those for the time being anyway. But it also means that you can't obviously haul these things out there to the job site scores of feet tall. They have to be manageable sizes because to do this efficiently, these plate assemblies have to be manufactured in a controlled environment somewhere off the job site. So it's envisioned that you'll go, for the most part, story by story, and there'll have to be connections at each floor, so that's what these straps represent here. And to create these flanged sections, you'll have to join these plate assembly elements together at intersections. So what follows, and I'm not going to touch on, time won't permit, but I'm not going to touch on all of these particular items, but as we worked our way through this, these are a lot of the details that we had to be concerned with as we worked our way through. I'll just mention along the way why we did the first couple of things that are up here. The transfers, you'll see when we get to the end, we can't do this thing even in our big laboratory at full scale. So we ended up, through a number of iterations, arriving at a test specimen, or at least elements in the test specimen that are approximately 3/8 scale. And that would still allow us to use realistic materials, material properties, and so forth, and be able to test it with the equipment we had available in the laboratory. Well, one of the things that ties together here, at least the first and the third item, one of the ways to make this go up rapidly is to be able to assemble a number of stories of these plate assemblies without the concrete on the inside, so you don't have to cast concrete as you go up every floor, either with the wall or the gravity system that's hanging off of it, and then you may be able to come in and cast a bunch of concrete at one time. Those plate assemblies have to be stable, standing there by themselves, and they have to be stable with the steel gravity frame system hanging off the side of it. So we needed to look at that, both what the limits might be, I'll say analytically, doing some calculations on the stability of the plate assemblies, and then the sponsor and MKA wanted this tested in the laboratory to see if we had agreement between what we had calculated and an actual test. So what was envisioned in the earlier slide that I showed, because there is a product out there, a proprietary product that already exists, for the transverse rods joined to the plates is a fusion welding process. That could not be reproduced here at this scale because they make it at one size and they couldn't adapt to make our specimens. So we had to come up with something that would replicate that. So when you see slides later on, you see bumps all over the plate, and that's because we used a double nutted process to put a threaded rod through the plates periodically, have a nut on the inside, a nut on the outside, jam them together to create in effect what would be what we thought a fairly rigid connection between the transverse rods and the plates. So I'm not going to show you this, but we did some little tests to verify that. We got data from that we could use in our calculations. A little bit you'll see what the stability test looked like. I'll gloss over that pretty quickly. And one of the other things that we did, remember in that earlier slide, I showed you from story to story we got to join these plates together. So what was envisioned was a strap that would have a fillet weld top and bottom, maybe not done at the same time. The first one put on, and then you use it as a guide for the next plate assembly that's lifted into place. Weld it up, and that's got to be tough enough to hang in there if this is cycled back and forth. So we did a test early on in one of our early specimens to show that with that connection we could yield the plates in shear and they would remain intact. What will follow, without going over every one of these while we're up here, then I'm going to show you some of the foundation details we had to deal with. Both of these really kind of relate to that. And then ultimately we get to what I'll call here a proof of concept wall test. It was really a final large test to verify that at least what we learned from some of this earlier stuff when applied to the design of our test specimen did indeed work. So this is a schematic of the stability test. The beams that are shown here are connected to shear tabs, so these represent the gravity system. These are actually much bigger than what would be in the real building. We weren't testing those. We were testing the wall here. This particular specimen has concrete cast up to a certain point. This is where there's a connection made between stories. I can't from this scale really tell where the other one is, but up here someplace is another floor and so forth. And this was while we were doing the stability test. The actuators that are kind of hidden off here on the side, but they're loading the beams to introduce the floor loads. And at least some of you over on this side probably won't be able to make this out, but this has buckled. It was an inelastic or an elastic buckling mode, and it pretty much verified what we had anticipated would happen. To get it to do this, it required multiples of what would be the service level loads out there, the construction loads during the construction process. I want to point out one other thing that I noticed from Jim's slides earlier that has changed between today and years ago. They're kind of hidden down here, but notice these students that are working on this. I noticed, Jim, in your slides, I don't think that anybody had steel-toe shoes on. There were no safety glasses, and there were certainly no hard hats. So we have evolved in that regard, too. Okay, the foundation details. I'm not showing a drawing here because the darn thing is so cluttered you can't really make out anything, and I hope the photo is not as bad as that. This is looking down in the formwork for our foundation, what represented a mat foundation that this wall would be founded in. There's some extra stuff here, the PVC ducts and the spirals. Those are to accommodate our tie-down rods that held this thing down to our strong floor so it wouldn't slip and slide around. It was restrained while we applied lateral loads to the wall. But the key thing here is in the background, there's a big heavy plate over here, and there's actually a pair of them. Welded to that are rebars on this side and actually on the other side too. They go down near the bottom of the mat and have big hooks on them. There are also shear studs that are attached to the plate. And we couldn't optimize every little component that was used in this system. So something like this base connection I refer to as a belt and suspender system for being able to resist the overturning moments from the wall specimen that ultimately ends up connected to it. There is also, and I'll mention these later, there's another duct back here and an anchorage. These are related to PT bars we use to simulate vertical load on the wall during the test. So the most critical one in here was this darn connection of bars to a plate, and there are procedures out there for that, but we needed to determine what did we actually need to do, so we didn't go to do this test, and we end up ripping our wall out of our foundation. So we did a lot of work in developing the welding technique to be used here, and these are a couple of examples, a poorer one, better one, where not only pulling these things to failure, but cutting them apart, etching them, and looking at the quality of the welds was part of the process in developing this particular detail. Then the other critical detail, where the dual plates attach to this hardware that is embedded in the foundation. When we got into this, we became aware of a test that was done in Korea not too many years ago, where they were trying to do something similar to this. And during the very first cycle of loading, with a detail quite similar to this, so the little skinny plate here represents one of our external wall plates. This big thick guy is the one that's connected to all of the hardware that's embedded in the foundation. And that is the connection between the two. In the Korean test, during the very first cycle that they attempted to go nonlinear, the welds fractured. That wouldn't have been a success. So we wanted to make sure this detail would work, and we wanted a fallback detail in case it didn't work. So ultimately, this is what we ended up using in our test. It performed greatly. We had no cracks in the welds that we could ever observe, and certainly no failure. Our fallback specimen was this complicated guy, and I won't try to spend too much time explaining it, but it is a redundant weldment. So we have a plate out here. Here's our big thick plate. We have an extra piece where there's welding down here. There's welding up there. There's an inner backing plate that would have to be there that spans around where some of this connection is made with an additional wall plate thickness. That was the just in case it fails when we start testing and we have to go back and retrofit our specimen to be able to complete the test. We were real confident this would work, but the folks at MKA said, well, don't use that in the test, because if you do, we take this to a building official, they say, oh, you got to use this guy, and it's going to be incredibly expensive. So we went with the simple test. Now, how do we verify those? There's a schematic of it and a test on the right. We just doubled up the plates so that we'd have a symmetrical loading, and imagine pulling on both of these and on this at the same time. Mounted these in an MTS machine. We did 40 plus cycles of load on these out to a strain of about 0.4 before we ever got fracture of the steel. And so we were convinced that these were going to work. Okay, finally, we get to call it proof of concept test. So there's a schematic of what our test wall looks like. There's a lot of stuff in here, but down here, that's that big heavy plate. It doesn't show all the rebars and stuff on it that we're connecting to. These little interruptions that you see here, these represent the individual stories and the straps that are used to connect them together. One thing that you can't see here, but you'll be able to see kind of in the plan view that follows. So this is a web, this is a flange, and in the intersection of those two, the corner, we have an angle that's welded on, and that has to be able to potentially make the shear transfer between that outer flange and the web. So the welds were important there also. We used a little bit different welding techniques and more control down here on the bottom where we expected all of the action, and a little bit more liberal work up here on top. Without going into detail, this is the apparatus for being able to load this, pushing and pulling relative to the wall. In plan, here's our wall cross-section. The little circles that you see on here are the locations of PT bars, unbonded, that we use to apply axial load to the wall to simulate the 40-50 stories up on top of the wall. And the other circles, the blue circles, are our tie-down locations to tie this down to our laboratory floor. Oh, here's the corners I was talking about where we have the angles that make the connections between the two sets of plates. And as I mentioned earlier, the transverse rods are shown on here. It's at least anticipated if this is built in the future. The bumps won't appear on the exterior of the wall. The architects were really excited about, I'm told, having these exposed steel on the interior of the building, something different. Okay, so very quickly, not going to show you blow by blow, but we put this together like the real thing. So this was the first story and concrete being placed. Once we got up above the ground, we had to have a working platform both for the students and the staff that are casting concrete, but also for the welder, the certified welder that did all of the structural welds. When we got up a little bit further, then we had to start bracing it off of the wall, and I always give my structural steel colleague a hard time. The bracing on this was certainly strong enough. I think it was a lot of overkill, but that's okay. We connected those two in the platform to what would be the shear tabs on the wall to handle the gravity load system. There's a little bit later as we work our way up, and you see the PT bars that ultimately we ended up stressing to use for vertical loads on the wall. And that was the day we did the final casting up there on top. Now, during testing, so the only thing that's changed here now is the platform's been modified a little bit because we had to get up here to make changes in the loading system as we would reverse directions, loading north and south, and I should mention that while I'm here. So if in the following slides you see anything that indicates north versus south, north is to the right, south is back towards the strong wall. And here was our response. And I'll stand up here and say, and we did something in hindsight, and when you look at some of the information that Sharon presented today, really stupid. We didn't have a flange on one end of the specimen. That's the stupid part. Because we had to control, or we had to set the depth of the specimen, which really reflected sort of a portion of the core wall, so that we could test it in the laboratory. So we had enough strength to be able to actually load this thing back and forth. And so if you look down here, this would be loading towards the strong wall, so to the south, and all this chatter that you see down here is when things started to fail basically in that web, because it was very large forces being concentrated in that concrete in the web. You'll see on a slide that follows up, before we got to this point, we also started to buckle steel on that end of the specimen. And that, again, it was a bad choice on our part to not put a flange on that side of the wall. We saw nothing like that when we went in the other direction, and the big flange was in tension. So when we would load the south side of the wall into tension, and we didn't have a flange out there, it put a tremendous amount of demand on the steel plates at that end of the wall. They went quite a ways out in the elastic range. When we load back in the compression direction, those things the cracks are trying to close in the concrete on the inside. The plates buckled, and then ultimately that's dumping everything into the concrete that was in that portion of the wall. There's the buckled plate on that south end of the wall. This is what some of the strain information looks like that we got out of those tests, and you can see loading in the direction where we had the flange, we were able to get out to some fairly large strains in the steel, obviously not nearly as far in the direction when we have the plates buckling. This is for the plates on the south end, so these are the compressive strains that were developed when this stuff started to buckle and the concrete crushed. And I'm almost at the tail end here. This, we lost on that south end our strain gauges once the plates started to buckle. They happen to be located right about where the buckles occurred. So this does not show the drifts beyond the 1%, but this is the distribution of strains. And feel pretty comfortable about the data. It looked very good. Over the depth of the section, this happens to be at 3/4, basically 1% and 1%. They're not linear, but the section didn't behave too much like the plane section that we think about all the time. Once we got done, we pulled off down there at the bottom just to see what was inside. We knocked all the bolts off, pulled the plate off on the outside, and the crushing extended in somewhere between 18 inches and 24 inches, and up this side about this far, also about 18 inches. So, as I said, this is preliminary. We're working on finishing this up now, but it wouldn't have been possible to do the last test unless we had paid attention and figured out along the way what some of the critical details were and refined some of those details. I stand up here with egg on my face. You got to have flanges on the walls. Those are basically the boundary elements for this type of system, and it won't work without it. And what we're currently doing right now, besides evaluating all this test data, which you just saw a flavoring of today, is developing a set of recommended design procedures. So if an office decides to take this and run with it, once you get approval from a building official, here's how you step your way through both proportioning the wall and the details that need to be used to complete the design. Thank you. I'd be glad to answer any questions you have.
Thank you, Mike. Fascinating concept and set of tests. Questions? Santiago, you were first.
Did you notice a difference between the lengths along which large inelastic strains took place on both sides of the wall, on the plant and on the web? You know what we call the plaster hinge?
No. Actually, yeah, a little bit of difference because our wall was unsymmetrical, so the resistance that we're getting in the two directions is different, but not radically different. Although we were able to push it further in one direction, and I think that's also what caused us to migrate a little bit further. But the inelastic stuff only went about that far up the wall. Okay? Was there two parts? Was that the first part or only part?
No, but it was the same on both sides.
Relatively, yeah, roughly, yeah.
And that's L over what? If I may put it there?
Probably about L over 2.
There was a question in the back.
Well, I'm going to answer based on what I've been told by the practicing engineers that we worked with. We cast ours in just from the top, and we went a story at a time. They're anticipating that they can pump, and I didn't mention, by the way, the mix that we used wasn't intended to be a self-consolidating high-performance mix, but effectively it turned into that, and it was 10,000 psi concrete. MKA anticipates what the contractors will probably, and they have talked with them a little bit, is that they'll actually put a port in their wall, and rather than dump it in from the top, they'll pump it in from the bottom. And they're thinking maybe as much as 3 stories at a time.
Okay. Mike, thank you very much.
Thank you.